Okay, so how is everyone today? Good, I hope? Not good? Okay, so we had an exam. That's good. On Friday night. It wasn't good? I think we should withhold judgment until the grades are back. So, you don't know? Not necessary to withhold judgment? Okay. Well, at any rate, the grades are scheduled to be back by Friday. Okay, so hopefully before, but there's a deadline on Friday. Good. So let's continue talking about differential equations. All right. So then, good. So this is a definition of separable. Separable. So I could say something like let. So in the first place, let function f from r squared to r be given. So an example of such a function will be something like f of x and y is equal to, say, I don't know, 5x y squared plus exponential of 5x y squared multiplied by exponential of 5y. So something like that. So this is the kind of function where you plug in, you've got two inputs. That's what is meant by r squared to r. You've got two inputs, and the real output is produced in that way. So whatever it is you plug in, that's what you get. So an example, for example, I could ask, how do you plug in, say, something like 2 comma 0? No, 0 is too easy. Yeah, we'll just do 0, since it's not really the point. So what am I supposed to do to evaluate f at 2, 0? Right, plug in x is 2 and y is 0. So this would be, 5 multiplied by 2 multiplied by 0, square that, and then plus exponential of 5 multiplied by 0, and then through the powers of arithmetic, that ends up being what? 1, right? Because that first term is 0, and then that's the exponential of 0, which is 1. Okay. So then, function f, is said to be separable if there are functions g from reals to reals and h from reals to reals such that f of x and y is equal to g of x multiplied by h of y. So in this case, separable means essentially that you could take that function f and you could factor it into two different functions. And this x1, the first one tells you all the action that has to do with x, and the other one tells you all the action that has to do with y. And this factor has nothing to do with x. Nothing to do with y, only x. And this one has nothing to do with x, only y. So such a function is said to be separable. All right, so then you might ask, how about that f? Can you think of a way to factor it into two functions, the product of two functions, such that one uses only x's and the other one only y's?
Yeah, second one.
Okay, you'd have to write it, you'd have to factor it into two factors, something multiplied by other something.
How do you do that?
Well, I'm asking, can it be done? And in the end, the answer is going to be no. No for this one. Because, we'd want to factor out, say, like the 5x there, right? We definitely want, if it were just that term, then we'd be good to go, right? One of the x function would be 5x, the y function would be y squared. But then when we add in this thing that only has y's in it, if we want to factor out the 5x, then we'd have to put a division by 5x with this term so that we don't modify it. So that one doesn't work. But for example, we could have one that looks like this. Say I don't know, p of x and y is equal to, let's think about it for a second. Well, let's not make it too complicated. How about just exponential of 5x plus 4y? Is it possible to, is this p separable? It is, right? It is separable because, well, we can use the laws of exponents, which is to say that because this is exponential of a sum, what can we do? Right, we can say that this is actually exponential of 5x multiplied by exponential of 4y. So notice that this factor only depends on x, not y, and that factor only depends on y and not x. Okay, and then you can imagine that instead of having just two variables, right, separable over two variables, if we had three variables, say x, y, and z, then something could be separable over all three, so that it would be a product of x, a function of x, multiplied by another function that's only a function of y, multiplied by another function that's only a function of z, etc. So this is separable. All right. So the differential equation. So the differential equation dy dx equal to f of x and y is said to be separable when f is separable. Okay, so then an example, or really the whole thing, is that if we say that dy dx is f of x and y, since f is separable, there are functions g and h. Since f is separable, there exists functions g and h, such that we can say that this is g of x multiplied by h of y, like that, right? And then now, remember that dy and dx are not functions, and dy dx, they're not numbers, so that's not a fraction. But the notation is a little bit suggestive, and you can in fact treat them somewhat like fractions. So if I solve for dy, then I get this, g of x multiplied by h of y dy, like that. No, dx I mean. And now here's the reason, or an additional reason, why this condition is called separable, is that, well, notice that concerning this equation, the left-hand side has just y's, but currently the right-hand side has x's and y's. And notice that if we divide both sides by h of y, then we get the following. we get 1 over h of y dy is g of x dx. So now, notice that this equation depends on variables x and y, but there's only y's on the left-hand side and no x's, and there's only x's on the right-hand side, no y's. So in such a differential equation, when you come to this state, when you come to this position, you've said to have separated the variables. Okay? And any time that you have a differential equation of this form, dy dx is f of x and y. If f of x and y is separable, then it's always possible to come to this separation. Now, the reason why this is a good place, is because, you know, just like when you're trying to solve equations, you can add a number to both sides, right? Add 3 to both sides. Or you can multiply both sides by 4, say. And you do all those things. One of the things that you can do to both sides in this context is you can anti-differentiate both sides. And the thing is that once given a differential equation, once you've come to this place, now you can anti-differentiate both sides. Okay. So, as a result, the concept of separable differential equations is going to be very important to us. In the end, it's sort of like the first kind of differential equations that we can solve. When you go on and you take a course in differential equations, you learn how to solve a variety of other kinds of differential equations, but to a large extent, at least the first techniques that you learn is ways to take an equation, a differential equation that's not separable, and to perform some kind of crazy recipe, and then say, oh, look, as a result of doing that crazy manipulation there that I learned, now it's separable. And then you do this. All right, so let's have an example. So let's solve dy dx is equal to x squared over y squared given that xy equal to 0, 2 is part of the solution. So now, concerning this right-hand side, x squared over y squared, is it possible to factor it so that it's a product of just x multiplied by a product of just y stuff? Yeah, it is. So in particular, we want to take this differential equation, dy dx equal x squared over y squared, and would you please, it's sort of so easy on this first one, arrange it so that you have all the y's on one side and all the x's on the other side. Okay, so it comes to this place. So y squared dy is x squared dx. So now we've performed a separation. And now that we've performed a separation, what can we do to both sides? We can anti-differentiate both sides. And now we can treat, you know, these problems separately. So what is antiderivative of y squared dy? Y cubed over 3. Okay, I'm going to get to that in just a second. And then what's the antiderivative of x squared dx? X cubed over 3. Now, I agree entirely with y'all that said we need a plus c. But do you observe that well, we're doing it twice, but we really only need 1 plus c. Why do we really only need 1? Right. So I could write a plus c for this side and another plus c on that side. But each of those constants are arbitrary. And then the difference of two arbitrary constants is still an arbitrary constant. So we only need one of them. So I'm going to write it just on this one side. So just one of them. Okay, now we could solve for y. So let's solve for y. So what would we need to do to solve for y? Okay, good. So then y cubed would be, if we multiply both sides by 3, then that would cancel that 3. And then we'd have 3 multiplied by c. Now the thing is that c is, again, an arbitrary constant. Okay, and then you multiply an arbitrary constant by 3. It's still arbitrary, right? It can be anything at all. So in a sense, you could just continue writing c, but that's a little bit sloppy. So I'm going to say that this is, how about C1, like that. Okay, and then if it was our desire to solve for y, then what now?
Cube root both sides.
Very good. So y. So again, sort of the way this works, x cubed plus c1. What's happening is that we want to get this y by itself, so we need to get this raised to exponent 3 to switch sides. And when you get that raised to exponent 3 to switch sides, when it switches sides, it becomes cube root. All right, interesting. Now, this is not entirely. This is most of the way to the answer, but there's yet more to do, because, for example, we have this information. So what is it we're supposed to do with that? What does this get for us? Yeah, that's going to tell us what c is. So now, to determine c1, we'll use this piece of information. So it's saying that when you plug in xy equals 0, 2, the solution, the equation should be true. So taking that equation and plugging in 0, 2, so 2 equal cube root of 0 squared, 0 cubed, not that it matters so much, I guess, and then plus c1. So the equation is supposed to be true. All right. So then 2 is equal to cube root of c1, and then it's probably obvious. What's the answer then? 8. Could it be negative 8? Why not?
Could be. Because you're cubing negative 8, negative 2, goes negative 2, 4, back to negative 8.
Thank you. Okay, so then remember, these radicals, they have a parity issue, which is to say the even ones, they squash the negative, the odd ones preserve it, right? Good. So then moving the cube root to the other side, 2 cubed is c1, so c1 is 8, and therefore now we've solved it. So the answer is that y must be cube root of x cubed plus 8. Interesting. Any question about this one? Yes?
Would we not solve for like c alone, or like are we satisfied with just c? Because it's like c1 is like divided by 3.
But it doesn't matter. In the end, it won't matter, because what you would do, you could, well, I'll say it like this. Go ahead and do it. So what would happen is that you would replace this c1 with 3c, and then it would turn out that c happens to be 8 over 3, and then you plug in, and then you plug in c over 8 over 3, and then multiply with 3 and get 8. Good. Other questions? All right. So a prototypical separable equation is in fact one that we already did. So so this one, dp dt, is equal to kp, okay, with a non-zero k, because otherwise it's kind of boring. So now the variables are different, right? Not x's and y's, rather p's and t's. Is this separable?
Because there's 3 variables.
But k is a constant.
Yeah.
It is. So in the end, sort of the question is that can you arrange matters so that you can get all the p stuff on one side and all the t stuff on the other side? So can it be arranged? The answer is yes. If in the first place we do this, if we say something like, well, dp is equal to k p dt, okay, then not separated yet, and then we could divide both sides by p to get 1 over p dp is kt, k dt, I mean. And k is just some constant. Now we've separated the variables. P's are on one side, t's on the other. Then you can look at last lecture or recently anyhow. We went over the solution to this. Okay, interesting. So now let's solve a particularly interesting one. So we solved this. What was it, last lecture? So a particularly interesting one of this variety is the following story. So I'm going to read it out loud, and then I'm going to write down this salient as a joke, but you don't understand it yet. We'll write down the salient things. So a tank, a big mixing tank, like, you know, imagine an industrial tank where we're having some chemical process, contains 20 kilograms of salt, and it's dissolved in 5,000 liters of water. And then we're pouring in some water into this tank, and that water coming in also has a certain salt concentration. Okay, but it's not the same as the concentration that's currently in the big tank. Then all of this is being mixed up very quickly, and the question is how much salt is in the tank at any given time. Okay, so it says a tank contains 20 kilograms of salt dissolved in 5,000 liters of water. And you're to interpret that as that 5,000 liters includes the 20 kilograms, right? Because when you pour in salt, it does increase the volume just a little bit, but that's not relevant. The volume of the solution is 5,000. So we've got some tank here. Okay, so then brine water, which is the name for salty water, with concentration .3 kilograms of salt per 1 liter of water is being poured in to the tank. at a rate of 25 liters per minute. Okay. So the solution is kept thoroughly mixed. And 4, water is draining out at the same rate as this is coming in. So water drains out. At the same rate. So altogether, the picture is kind of like this. That we've got a tank. Okay, so that's my artist's impression of a tank. That's the water level. And then, you know, there's some mixing element here. This is like the mixer, you know, and it's turning. It's keeping this all very well mixed. It's got some salt in it. From an external source, there's water coming in. It's being all mixed up, and there's water leaving. And we've arranged matters so that the rate at which the water comes in is the same as the rate at which the water goes out. So now, here's the deal. We're going to set up a differential equation that solves that answers this question. But before we do that, I want to give you sort of an idea of what's happening. Suppose that you are trying to get a bath ready for yourself, okay? And already there's water in the tub, okay? And let's say that in fact it's at the right level. Like you don't want there to be less water, you don't want there to be more water, but the temperature is just too cold. Okay, it's just too cold. Okay, so in the tub is enough water, but it's cold. One way you can get the bath ready for yourself is, let's say that too cold means, say, like 10 degrees Celsius. Okay, and then warm enough, say, is maybe 40 degrees Celsius. You like to take a really hot bath. I guess it's not really all that hot. But you want it to be 40, and it's currently 10. Well, one way to do it is that you can start pouring out water that's 40 degrees Celsius out of the tap. And then you can also open the plug so that the water coming in, the amount of water coming in is the same as the water going out. So what will happen to the water level? Will it change or what? It won't change, right? The water level.
It's the same rate that's coming in, though.
Right. So we're arranging it so that the amount coming out of the tap is the same amount that's draining. So the water level won't change. But suppose that hot water is coming out of the wall and you're keeping it really mixed up. Can you see that the temperature of the tub will gradually increase until it's the same as the water coming out of the tap? Similarly, what if it would in principle take infinitely long if the tap water was 40 degrees Celsius and that was what you desired for the tub, because it would slowly, asymptotically get up to 40 degrees. Another way to achieve 40 degrees would be to take 90 degrees Celsius water coming out of the tap. Now that's way too hot to bathe in. Okay, but if 90 degree tap water is coming out, you're mixing it up, and you're pouring out water, then the temperature is going to increase. and there's going to come a point where it's exactly 40 degrees. So does everybody understand the idea? It's the exact same here. We've got some, except instead of saying heat, we're saying salt. We've got a tank. Okay, we've got a tank. It's salty. More salty water of a different concentration is coming in. We're mixing it up, and stuff's draining out. How much salt is in the tank at any given time? It's the exact same question of how hot is the bath water. It's exactly the same. Now, one thing I want to mention is that in actual fact, in this process, what happens is that the saltiness would be sort of higher here and lower here because the mixing is not instantaneous, right? So the salt concentration would not be uniform across the whole volume, but we're assuming that it is in fact uniform across the whole volume. Now that assumes that information travels infinitely quick, which is false, okay? Because causality travels exactly at most at the speed of light, right? But here we're saying it's instantaneous. All right. So we need to come up with a model for this. So for the volume in the tank, volume, I'm going to use the letter V for volume. Okay, for the salt mass, what letter do you want to use?
MS.
M? Okay, M's good. And the question is how much salt is in the tank at any given time? All right, and what we're going to do is we're going to figure out, okay, how is the rate? How is the amount of salt changing? Okay, so then M, that's the amount of salt. What we want is dm dt. Okay, so then we want dm dt. Now let's consider, because salty water is being poured in, that means that we have a source of salt. And because salty water is being poured out, we also have a sink, which is to say a place where salt is being lost. So we have a place where salt is coming in, and we have a place where salt is going out. So structurally, what this should be is this should be the rate of salt which is coming in, and then subtract the rate of salt going out. All right. So let's address this. So how can we address it? Let's think. So the rate at which salt is going out. So what's the concentration of the salt? Let's think about this. If it's going to be the rate of salt in minus the rate of salt out, this first factor should be the concentration coming in multiplied by the rate of volume in, and then this one should be the concentration going out multiplied by the rate of the salt going out, rate of volume going out.
Volume going out means salt going out, basically?
No, volume of solution. Right. How fast is the solution coming in, and what's its concentration? Okay. So let's think about it. Do we know the concentration coming in? We do, right? That was part of what was stated. So it says 0.3 kilograms of salt per 1 liter of water. So that's the concentration coming in. So 0.3 kilograms of salt per 1 liter well, not water, that's not really good. It's really 1 liter of solution, because we're ignoring the volume of the salt, really. And then how fast is it coming in? 25 liters per minute. Okay, so that's how fast salt is coming in. Now, let's do some unit cancellation. Do you observe that the liters of solution, that cancels? And as far as units are concerned, what we have is kilograms of salt per minute. Okay, good. So now what's the concentration going out? Now this is the tricky part. This is the tricky part. Because as this procedure is going, right? As we're running this procedure, the concentration is changing in time, right? That's the whole point. Okay, and what is the name for any given time that we gave to how much salt is currently in the tank? M. And what is the name at any given time that we gave for the volume in the tank? V. So what's the concentration? M over V, right? M over V. So that's the concentration that's in the tank at any given time. And how much solution is leaving the tank? Right, 25 liters per minute, because that's what the story said. All right. So simplifying this and dropping the units. So in the first place, do the units of this make sense? So what are the units of V? Liters of solution, right? And then that cancels with these, so that we have kilograms of salt per minute. Yes? Yes, thank you. 25. Okay, so then we have dm dt is, well, 0.3 times 25 is what? Zero 0.75, right? Is it? Let's check that. Or is it 7.5? 7.5. So that'd be 7.5. That's that first term. And then subtract, what? 25m over v. Okay, ignoring the units. All right. So now, currently in this equation, how many variables are there?
3.
There's 3 of them, right? There's m, t, and v. Yes. Well, that's why I wrote this subtraction.
Oh.
I could have written add. I could have written add, and then this would have been negative, and it'd be the same. So 3 variables currently, m, t, and v. And we're only going to be able to proceed if we can eliminate v. Okay, because in the end, all that we're interested in is m as a function of t. So is it possible to eliminate v? Okay, how?
Well, V is going to be a constant, right?
V is a constant. Why is v a constant?
The amount in the tank never changes.
Right.
Right. So remember, volume represents how much is in the tank, and then you've got to read the story and realize, oh yeah, we started with 5,000 liters of solution, and things are so arranged so that the amount of brine water coming in is the same as the amount of tank water going out. So in fact, V is not changing. V must be constant. Yes?
Since V is given 5,000 liter,
Mm-hmm.
can we not just substitute for 5,000?
Well, we're going to. But in principle, understand that it could have said that we had an enormous huge tank, and we started with 5,000 liters, okay, And then this is coming in, say, at 50 liters per second, or per minute, I guess. And then this is leaving at 40 liters per minute. And then in that case, the volume would be changing. But in this problem, the volume is not changing. Okay, so then V is constant in time. And therefore, we know that V is just 5,000. So that we have this. dm dt is 7.5 minus, what, 25 over 5,000 m. All right. Any question about how we got there? Is this okay? All right. Then now what we want to do is, can we separate this? Can we do it? What do you think?
By dt.
Okay.
Do I
So
subtract the
let's think here. So I'm just copying, not doing any work yet. So well, I guess I'll do a little bit of work. So I can cancel something there, right? So that'd be what? 1 over 2, 1 over 20? No. 40? Let's check that. Oops. 200. Okay. Wow. How was I so off? Okay. So this would be 1 over 200 m. Okay, then moving the dt over, we have 7.5 minus 1 over 200 m dt. So can we get all the m stuff together and all the t stuff together and separate them? How do we do it? I can just divide by that thing, right? So that we have 1 over 7.5 minus 1 over 200 m dm is just a regular old dt by itself. So did we separate it? We did. Right? M's are together, no t's. T's are together, no m's. So we did it. All right. So then from here, what do we do? Anti-differentiate. Okay, so then antiderivative of 1 over 7.5 minus 1 over 200 m dm is antiderivative of dt. The right-hand side is easy enough. Do you observe that that if we were to do a substitution, say u is equal to the denominator, then basically we would have this negative 1 over 200 come out as a factor in the substitution. So I claim that when you're comfortable with this, you can anti-differentiate the left-hand side doing the substitution in your head. So what is it? Okay, so it seems to me we're not comfortable enough. So I'll say W is 7.5 minus 1 over 200 m. Okay, so doing that, then we would need dW. So the 7.5 goes away, right? Differentiates away, and then we'd have negative 1 over 200 dm. And then now I'll move that to the other side and get what? Negative 200 dW is dm. So that tells us that that antiderivative on the left would become 1 over W multiplied by what? Negative 200 dW? Okay, and then ignoring the negative 200, what's the antiderivative of 1 over W dW? log absolute W. So this would be negative 200 log absolute W, and then equal to, what's the antiderivative of the right-hand side? T. But we're going to need a constant somewhere, so I'll write T plus the constant there. Okay, now we want to solve. So then this would be log absolute W is what? So I want to divide by negative 200. And then dividing that constant by negative 200 is still an arbitrary constant, so I'll just write plus C1 because it's just some constant there, right?
What about this sign?
It's still arbitrary, right? What this means is that means any real. And if I take any real and then divide it by negative 200, that could still, in principle, be any real whatsoever. So then how do we get W by itself?
Raise it to the power.
Exponential, right? So absolute W is exponential of this mess here. All right. So then now if we want to get W by itself, oh, wait a minute, we've still got to get back to we've still got to get back to this, right? Right? So then now we can get to here and say that that's absolute 7.5 minus 1 over 200 m, like that, is that. Now I'm going to move this C1 to the front, so this would be exponential of C1 multiplied by exponential of negative 1 over 200 t. All right, now let's think about this for a moment. Let's think about this. We need to know what will, how could we get rid of the absolute value? So how do we do it? I'm sorry? So on the one hand, we've got plus or minus, right? What we're saying is that, in a sense, there's two possibilities, because absolute value of this thing is that thing. So there's two possibilities. That 7.5 minus 1 over 200 m should be plus or minus that thing, exponential of C1 multiplied by exponential of negative 1 over 200 t. But now let's consider C1 can be any real number. How about exponential of C1? Well, if you take any number whatsoever, any real, and compute its exponential, the result is positive, right? But now what we're saying is that, in fact, it's going to be plus or minus. So C1 is any real. Exponential of C1 is any positive real. And then now we're saying plus or minus, so now we have any negative or positive real. Okay, so then what I'm going to do is I'm going to say, in fact, that's just another arbitrary constant there. All right. So 7.5 minus 1 over 200 m is C2, exponential of negative 1 over 200 t. And now, can you see that we can solve for m? We can solve for m by moving the 7.5 over and then multiplying by negative 200. So I'll do that quickly in one step. So what would that give us? So, well, it would be negative 200 multiplied by C2 exponential 1 over 200t, and then moving the 7.5 over. So I will multiply those out, and notice that we have negative 200 times C2, and C2 is an arbitrary constant, so that's yet one more arbitrary constant. So this is m is equal to C3 multiplied by exponential of negative 1 over 200 t, and then what's the product of those? $1,500. All right. So now, how do we figure out C3? So how to figure out? So if you look at the previous exercise, what I'm telling you is that the place that we are at, analogous, is right here. So in the previous exercise, we came to a place where we said, well, and how can we figure out C1? Well, how did we do it? We use that information, right? So what the information that we need is we need to say that in fact we do know how much salt there was at some time. So you look back at the statement of the problem. So this means that when the process began, that is to say at t is what?
0.
At t is 0, we knew that m was 20. So we can plug that in. So then that tells us that 20 should be equal to C3, and then t is 0, which means that that's just exponential of 0, right? And then plus 1,500. And now we can solve for C3. Of course, exponential of 0 is 1. So what's C3 then? Negative 1480. Okay, therefore, we can answer that m is in fact negative 1480 times exponential of 1 over 200 t plus 1,500. Okay, so last thing is that consider this number 1,500. Of course, it's not going to change in time, and that coefficient right there, that negative 1480, that's not going to change either, right? And this exponential, what's going to happen to it? So it's negative 1 over 200 times t. So what's going to happen to this? This is going to go to, where does this go as t goes to infinite? Well, where does where does this go as t goes to infinity? It goes to 0. Right? This exponential thing is going to go to 0. So if that exponential goes to 0, then that whole factor goes to 0. This whole thing will go to 0. So at infinite amount of time, there will be that much salt in the tank. But I want to explain to you that that's completely natural. Because if you wanted to take a bath, okay, and the water was too cold, okay, and then you turned on the tap with the water temperature that you want, warmer, and mix it up, then after an infinite amount of time, the condition of the water in the tub is going to be the same as the condition as the water coming out of the tap, right? That's what the tap is giving you. Now, if we wanted to answer the question, how much salt is there at time 45 minutes? Well, then you just plug in 45. T is 45. Okay, have a nice Monday.